guess you get a little bit of a different flavor here of a graphical user interface. I'm not going to be bashing the building Tickle. I think it's a great development too, and they both, I mean, both graphical interfaces have different purposes, and you just pick whatever you like. This is a fairly old presentation. I just updated a few slides in here. OpenSees Navigator, the graphical user interface, it was developed by myself, a colleague of mine who's now a professor in British Columbia in Vancouver, and then another postdoctoral scholar that we had over here for a while. His name was Ichi Kohama. He's now back in Japan. So Ichi did most of the geotechnical stuff, and then Tony and I did most of the structural work in Navigator. So it's MATLAB based, and it can do the pre and post processing for OpenSees and also OpenFresco for those people that are interested in doing hybrid simulation and are using OpenFresco. So it can do that side as well. That's a nice added feature that you have with OpenSees Navigator. It has a bunch of design toolboxes built into it. If we have enough time, I'll quickly show you what's there. You can download this as both either P code to run under MATLAB. So if you have a MATLAB license and you just want to run it directly in MATLAB, you can download it as P code. Or if you don't want to install MATLAB on your machine, there's also self-executable versions available for both Windows and Mac. And so far, we are like on our website, we are having like Google tracking, and we're kind of seeing who is using it, and it's fairly widely used throughout the world. The motivation was to actually replace the Tickle text input. Tickle text input is very powerful, as you probably have learned today, if you do programming approaches to building your model. But sometimes for very simple stuff, when you're just trying to get started, it's nice to have a graphical user interface and not to have to do everything in Tickle. So both have their valid application, the Tickle input and the graphical user interface. Most researchers, when they use OpenSees and they do their research or their experimental tests, and then they use OpenSees to try to model stuff, they're already using MATLAB to do all the post and pre-processing. And so typically that's why we then decided to go ahead and basically do it in MATLAB, even though MATLAB is a little slower than directly doing everything in Tickle. But a lot of people are very used to the MATLAB interface and all the functionality that is available in MATLAB. So with that, I'd just like to show you what Navigator can do. I have a bunch of slides, I'll go through them fairly quickly. You can do very simple models, just frame element models. You can then do 2D structures like braced frames. You can do shell structures in OpenSees Navigator, or 3D building structures, or you can do whole bridges like that. Or that's the last thing I just updated this afternoon, where one of the students over here at Berkeley is currently using it for the nuclear industry, where we're looking at nuclear power plants that are base isolated, and she is using OpenSees Navigators to do a lot of those analyses. And you can see you can build fairly big models using OpenSees Navigator that have mixed applications. So you have frame structures above, but then you also have solid elements below. So it can do both. There's a bunch of templates available in Navigator, so that's how you would start up. You'd go up into your menu here and basically go into the file menu and create a new model either from a template, and then you would select what template you want to use to set up your model. And for example, if we wanted to set up a zipper braced frame model, we would see a mask like that, and then we would put in all our parameters, number of stories, number of bays, and so on, and then we would be able to generate that braced frame. That would look something like that. Another way which people have found pretty useful, I think, is a lot of people, especially in the industry, are using SAP 2000 to do their analysis. And so we have a interface written in OpenSees Navigator that can convert a SAP model as much as possible. It cannot convert every single thing over, but it can clearly convert your geometry over, and it will try to do everything else that it can do. convert it into OpenSees Navigator, and from that then you can run your OpenSees model. So if you use that conversion capability, like I highlighted here in red, carefully check the model after you convert it, because there is no one-to-one relationship obviously between SAP 2000 and OpenSees. The way you would go about it is you would go into SAP 2000, you would export whatever model you have, and I'm showing this for this nuclear power plant model. You would go up and export this into an S2K file and select the whole geometry, all your assignments. So this is a SAP interface that you would see when you do this export. And you would make sure that you select everything, select all your load patterns, and export that. So you get then an S2K file. And then you open up OpenSees Navigator, and you go into open the model from file, and select that S2K file that you exported in SAP 2000. And basically what it does, it imports everything, so you'll get the geometry in, you'll get materials in, elements, all your loading, and then you go through and double check stuff before you run it. So that's a pretty nice thing. Another thing you can do once it's imported, you can look at the geometry of your model. So you can, for example, go into XY planes if you just want to see different stuff in different plan views. So you can go into an XY plan view, and then you can use those arrows to flip through the different plan views. You can do the same for elevation views. You can do that and flip through them. There's a bunch of options similar. The whole OpenSees Navigator is, if you know SAP, it looks fairly similar. So you can show properties of your model, nodal properties, element properties, and some general properties, and you can turn that on and off by using that interface. So for example, like this, you would then have a model, and then once you have it in and you still want to go and basically now edit the geometry of your model, you can do that by, on the nodes, you can add, delete, or move nodes around. And on elements, you can do the same. You can add, delete, you can divide or join back together different elements. And you can also add zero-length elements if you try to put hinges and stuff like that into your model. Once you have your whole geometry defined, you start defining all the other necessary properties that you need to assign to your model, right? So you learn this whole day now, all the different classes that we have in OpenSees and what you need to define. So inside the define menu, all you basically need to do, you start at the top in your define menu and you march down. So you start with materials. So you go ahead and you define your materials. And we have all the material templates pretty much. We try to keep it more or less updated. So whatever, when new materials get into OpenSees, we try to keep it updated with OpenSees Navigator as much as we can. So we have all these templates available, so you would go ahead and select one of those. So for example, if you wanted to define a steel 01 material, you would go in, a mask will come up, you give everything in OpenSees Navigator a name. So inside OpenSees, everything has a tag, as you learned today. In Navigator, you'll have everything by name. Yes?
OpenSees Navigator is in OpenSees.
No, it is written in MATLAB.
So you have to have MATLAB license.
That's what I was trying to say at the beginning. So there's two versions available online. Either you have a MATLAB license and you download what is called a P code. So it's like M files in MATLAB, but you don't see the source code because we don't want to release it yet. Eventually we might do that. Or there's a self-executable version available. So then you don't need to have a MATLAB license. It's just an exe file. And you need some library, and that's available too. So you install the library first, and then you execute it, your executable exe file. Or if you're on a Mac, we have that too. And then you can run it without having a MATLAB license. So everything will be by name in OpenSees Navigator. So you give your material a name so you can find it again later. And then you'll put in all your properties. Same as what you do in OpenSees, but do it through a mask. And then you can come back once you have it defined. Then you will see here, okay, I have now my library of materials that I'm defining, and you can basically find them again. Same thing for ND materials, so if you want to do solids and stuff like that, we have all the different templates available for ND materials. Then you go one step down, after you have all the materials defined, you go in and define your sections. So we have sections that you can do line sections, for example here, different templates, same story. For example, you want to do an elastic section, you go in, put the properties, give it a name, or if it's a 3D model, it will automatically change your mask depending on if you're in a 2D or 3D model. So in a 3D model, you'll have to put in the rest of the properties. Or then if you wanted to define a fiber section, for example like this, a mask will come up and you can add stuff fiber by fiber, like up here, or you can do it by patches, and then you can put layers for the rebar. So define that and put it together. So for example, then if you come in and you want to define your core concrete in our section, so if I want to do the inside part here, then I would come in here and basically go back to the materials. So all the materials that you defined previously will now show up as names there. And you just select it, put in the rest of the properties, generate your patch. For the steel section that was inside that cross section, at the W24x68 for example, you can actually load that in by name. So it will go into the ASC database and it will discretize that section for you automatically. So you don't have to go and figure out, okay, what's my flange, what's my web, how many fibers and so on I want to do. You can do that automatically and will read in from the ASC database, it will read all the cross-sectional properties, figure out how it needs to do the discretization. Then we also have sections that you can define for areas, area elements. So if you want to do quadrilaterals or shell elements, so we have all those sections available. Same story, you define those. And then once you have all the sections, you have the materials, you have the sections, next thing you go and define the elements. And same thing, for elements we have line elements, we have area elements, or we have solid elements. So here I'm showing the line elements, and all the different elements that are available in OpenSees are available in OpenSees Navigator as well. So for example, if you wanted to define an elastic beam column element, you would come in, the mask will show up, and again, you can load properties from the database. So you can click on the database button, and it will go in, and you can figure out from the ASC database what the properties are. So you don't have to go and open up the book and look everything up. Or if you do a force beam column element like this, then you would come in and tell it what are the number of integration points that you want, what are the section type that you previously defined, you will load that in, and then you can put optional arguments for this element, for example. Same thing for area and solid elements, so you can see for area elements we have the quads, the enhanced quads, the SSP quads, we have the different shells, and then also a bunch of different brick elements. So if you want to do geotechnical problems with OpenSees Navigator, you can do that as well. So now that we have the material sections and elements defined, let's go ahead and do our loading. So again, you go to the next step in the define menu, you come down, which would be the time series. Like Professor Philippe was showing, we need time series when we do loading, and then the next thing would be the load patterns. So you come in and define our time series, and you have all the templates available that OpenSees has. So for example, if we wanted to do an earthquake analysis, we would have load in a time series from a file, for example. So that's called a pass file time series. And you basically click on the browse button, figure out where that file is on your machine, and load that in. If it's a recognized format like NGA database or something like that, it will automatically load in the time step for you. If it doesn't recognize the format, it will leave the time step empty and you have to type it in by hand. Another thing, once you have all your time series loaded into Navigator, there is a function that you can plot them, so you can actually look at them and see if that makes sense. Once you have the time series defined, next thing you will have to do is the load pattern. So you go one step down in the define menu, click on load pattern, and you will get the different templates for your load pattern. So if you do static analysis, you would pick the plain load pattern. If you did a ground motion analysis, you would use the uniform excitation, or if you had multiple support excitation problem, you can do that too with OpenSees Navigator. So here I'm showing, for example, defining a uniform excitation load pattern. All you will have to do is tell it what time series you want to use with that pattern and what direction the ground motion would be in. So now we have all that defined. We have the geometry done. We have all our material sections and elements. We have the loading. Now we need to decide what do we want to record while we do the analysis. Same as in OpenSees. So we have a menu for defining recorders, and there's a couple of templates already there. So if you want to the whole deformed shape of your structure, that's there by default. Reaction forces, that will be recorded by default as well. And if you want to do if you had a dynamic problem, you want to do an eigenvector analysis, figure out what your modes are, that one is there as well. So there is some default recorders, and then there's a bunch of templates to add other recorders as you see fit or whatever you need. So for example, the node recorder, this is the default that is already there, called deformed shape. And as you can see, it will record displacements, velocities, and accelerations for a dynamic problem. If you had a static problem, it will only do displacements. And it will do that for all nodes, so that we actually can plot the deformed shape later of the model. If you have a really big model, that might not be a good idea. It might generate a lot of data on your hard drive. So then you might want to go in here and modify this and maybe only record certain nodes that you're interested in. Same thing we can do for element recorders. This is the mask, for example, for a beam column element recorder. You can record global forces, local forces. You can go all the way down into the section and record section arguments, forces, deformations, or even further, if your section then has different fibers, you can go all the way down into your fiber and record stresses and strains in the fiber. So that's the recorders. Now the final thing is analysis options. Same thing as when you OpenSees. In OpenSees Navigator, you now have to define how are you going to do your analysis. And again, there is two defaults there. So there's a static default there, and there is a transient default there. So you don't have to know every little detail on what to do exactly for the different analysis options, so you can use the default. But if you wanted to go in and basically decide for yourself what to use, you can see all the different classes that Frank must have talked about today already. So you basically go ahead and tell it what analysis type you're doing. For example, a transient analysis. You'll have to tell it how are the constraints enforced. So you have your constraint handler. This right now has probably that model I'm showing here has only single point constraints. So you have a plain constraint handler. Then integrator type. There's a lot of different integration methods. The one I'm showing right here, right now, is for a hybrid simulation that I was doing. So you have an alpha operator splitting integrator that I'm choosing for hybrid simulation. And that specific integrator needs a linear solution algorithm. That's why I'm having a linear solution algorithm, not a Newton-Raphson, for example. Then I'm doing the convergence test, which becomes useless in this case, because I'm doing a linear algorithm. I don't need to check convergence. But if you did a Newton-Raphson algorithm, regular dynamic analysis with, let's say, Newmark method, for example, not what I'm showing here, then you would have to decide, okay, how do I check on convergence? Do I check energy? Do I check on the unbalanced forces? Or do I check on norm displacement increments? Then you have the DOF number. So right now it's not renumbering the degrees of freedom. So that can be beneficial to solve your system of equations faster. And then you have the system of equations itself. So you kind of have to think about, okay, how is my A matrix looking? And right now I have a very small problem there, so I'm just using a band general, not very optimized, but the problem that I was running here is so small it made no difference. So I have everything defined. Now I need to assign everything that I have defined to my structure, right? So I go 1 over from the define menu on the top there, I go 1 over into the assign menu, and I start marching down again. So I start assigning stuff to the nodes, like my boundary conditions, the single point constraints. If I do have multi-point constraints, I assign those. I send masses if I have a dynamic problem, the loads, displacements, or if I do multiple support excitation, I have to assign imposed motions. Same for elements. I will go through, I'll assign element types to all my different members. I'll have to assign for the frame elements, like Professor Filippo was showing, all the geometric transformation class that we have in OpenSees. So I go through and I assign to all my different frame elements. Okay, am I doing a linear geometric transformation? Am I doing p delta? Or am I doing a co-rotational transformation? So you assign that. Then if you have a 3D problem, you want to assign your rotation of your elements. Are your columns oriented 90 degrees? Are they oriented 180 degrees? So you assign that with rotations. You can modify local axes if you like, and you can also assign loads to the elements that allow you to assign element loads. So for example, I'm showing a few here. Nodal masses, the way you would assign it, you will type in whatever node numbers you want to assign it. You can do multiple node numbers at the same time, and you would put in your mass values. If you wanted to select, for example, all your nodes at a certain plane, you can click on the select button, give it an x coordinate of 240, so then you'll find everything in your model that has that coordinate and select all those nodes for you automatically. And then you can do similar things to assign element types or to assign geometric transformations. And because this is all programmed in MATLAB, so in all these input masks, you can do operations that you're very familiar with. If you know MATLAB, you can say, okay, I want to assign everything from element 17 to element 24. So you can do these operations and it will understand it. You can do formulas too. So if you needed to put in your mass there, and you know it's like 5 kips, you can do 5 divided by 386, and it will do that. Once you have everything assigned, you can double check if you have the right stuff assigned. So there is the whole display menu in OpenSees Navigator that you can look at node numbers, you can look at your masses that you have assigned, your element types, your geometric transformations, everything. Then, last thing we need to do before we can run an analysis is define an analysis case. And again, we have two defaults. So we have a static default case and an eigen default case. For example, if we go into this here, what am I doing here? Let's see. Oh, actually, that's a dynamic. Okay. So I'm showing how it would look, how you would define a new analysis case if you wanted to do a dynamic analysis. So one of the two defaults that was not there, the dynamic. So, for example, you will give it a name. You can do sequences of analysis. So it will figure it out by itself. So you will basically tell it what was my previous analysis. For example, this one was an experimental test that we were trying to replicate, where they ran some white noise before they actually did the ground motion. So I would start from that white noise, and then I would select the load pattern names. So I have my earthquake 1 that I would select there. If you have multiple earthquakes, like you have excitation in X and Y and Z, you would be able to click all of those. So just hold down your control key and select different load patterns at the same time. Then you choose what your recorders you want to use in this analysis case. Again, you can click whichever ones you want to use. Then select the analysis options that you have previously defined. So obviously you're doing a transient analysis, so you've got to select the options for a transient analysis. And then something really nice that you can do, because this is all happening through the graphical user interface, and you're sometimes losing that capability that you have in OpenSees when you do stuff in Tickle scripts, where you can like control your whole analysis and do one time step. You analyze one time step, and then if it doesn't work out, you change your solution algorithm, you change your convergence test, and so on. Usually that's kind of hard to do through the graphical user interface. So the way Navigator does this, you can load in an additional user-defined analysis script. And I'll show you what you would do. You basically type in your while loop. going through the analysis what you want it to do when it doesn't converge. So that's what you load in there. And then you can define damping parameters, all the Rayleigh damping parameters if you need to do that. If you do geotechnical problems, you can define additional geotechnical parameters. You put in the number of load steps and the time step increment that you want to do your analysis. For the damping parameters, for example, defining the Rayleigh damping parameters, you go in, you get this mask, you can click on calculate where you can put in you basically choose if you want to do stiffness proportional, mass proportional, or Rayleigh damping, and you type in your values and it will basically calculate the curves for you and display for you what the different contributions are. And you will see the two corner frequencies that you selected. So you can kind of see what kind of damping, because Rayleigh damping is sometimes tricky to really figure out a good amount of damping for your higher modes and your lower modes, and how do you do it, where do you pick your corner frequencies. So this will help you do this. This is probably hard to read, but this is a user-defined analysis script, like I was saying, that you would load in. So this would be general, the way you already learned it this whole day today. You would write your tickle script, do some kind of while loop here, and basically do one analysis step at a time. If it fails, switch your algorithm. If it fails again, switch again, and so on. So that then you really get the control over the whole analysis like that. So now we're basically ready to run. So like I said, Navigator is just a pre and post processor. So we have everything defined. It's unlike Tickle, building Tickle, where you run inside building Tickle. This is different. So this whole graphical user interface will now write the input files for OpenSees. So you have to tell it where is OpenSees located. So that's the first step. You do that just once when you download the program. And then once you have told the program where OpenSees is on your computer, it will remember. So you do this once. Then you click on this button up here, like right there, for writing the Tickle files. And so it will write all the input files for you. And you can actually go and look at them and modify them if you wanted to before you run it. Or you just go ahead and then you click on the run button, and it will basically, you have told it before where OpenSees the executables is sitting. So now it will call that. It will source in all these files that it writes for you. It will source those in and run the analysis for you. When it's done, you want to load, because now, so we've done the pre-processing, and then OpenSees has done the analysis. Now we want to do the post-processing in Navigator. So we got to load all the results that OpenSees is producing back into the graphical user interface. So first thing you will do, you'll click on the green button on top, which loads the OpenSees results, and the mask will show up where you can select. It will show which analysis cases you have actually run, and you can click on them, which ones you want to load into OpenSees Navigator. So then you get a bunch of new menus once you have it loaded in that will activate, like up there, and which will now allow you to plot the deformed shape of the structure, and you can animate this, or you can just scroll to any time step in your analysis. You can select if you want to plot this as linear shapes or cubic shapes. You can put in some magnification factors there, and then you can animate it or just go to a certain time step and look at your deformed shape. You can do similar things to look at forces. So you can look at element forces. Here I'm showing axial forces in all the members. You can do, if you did a dynamic analysis, you have some structure with mass and stiffness, and you did a modal analysis on that, you can look at your mode shapes and your eigenvalues and plot that, and you can also animate it. Or you can go in and plot any quantity that you're recording against any other quantity. So there's this plot interface menu that allows you to come in, select your analysis case, and then select anything on the x-axis versus anything else on the y-axis and plot it. So for example, here I'm selecting the recorder called deformed shape, and I'm plotting time on the x-axis, and then again selecting recorder deformed shape, selecting displacement, node 16, degree of freedom 1, and then I'm plotting that. And the kind of, so like this I can plot many things on top of each other. And there is a bunch of other menus. If you go under display there, you can generate FFTs of your signals and stuff like that. You can filter things, like a lot of additional functionality that might be helpful when you do your analysis. Another nice thing what you can do is and we actually are using this a lot, is the nuclear power plant project right now. One important part in a nuclear power plant is floor spectra. So we are actually not just the response spectra at ground level, but we are really interested in looking at floor spectra because of all the equipment that you have inside a power plant. And so one nice thing that you can do with Navigator is you can define response spectra. And you can use any node in your structure and then select that node and the degrees of freedom, and it will pull out the absolute acceleration and generate the spectra for you. And so you can plot the spectra very quickly like that and do comparison. You can animate the response. This is an example that I'm showing here where I was doing an analysis of an unattached rooftop solar array. So this is a solar array, the deformed shape under uniform wind loads. You can animate, and it's showing just the coloring right now is the vertical displacement. This is another one where it was actually attached. And so we had attachment points where we're holding it down, and then where it's really red, there was nothing there holding it down. So the wind was lifting up the array. Like I said, we can do geotechnical problems. So here we have a soil column with, that is saturated, and it has a slight incline. So you'll see it starts, we're shaking it at the ground, and has, I think, I forget right now, 4% incline or something like that. So it tends to always try to go towards one side. And the colors that you see going up, that's basically the pore pressure that is generated. And when it's going towards the red, that's when you start having liquefaction in your solar column. And so you can animate that with an OpenSees Navigator. So we can do that. We can show if we do, again, for geotechnical problems, or not just geotechnical, anything with like quadrilateral elements, we can show the principal stress and strains, and we can animate that. And so, I don't know, do I have a few more minutes, I guess? There's a few like design toolboxes that we have available in Navigator too. So there's an AIC design toolbox, which allows you to do a few different things. I have listed them on the side there. You can just look up available sections from your steel manual. You can find section properties by matching certain criteria, and then you can do design checks. You can do bending capacity, compression capacity, shear, or even PMM interaction capacity checks. So here I would show, for example, looking up certain properties. So you need to have your steel manual with you. So you can look up what the properties are of a W24/68 if you wanted to do that. Here you can find matching sections by giving criteria. So you can go in and say, okay, I want to find all my W sections that have a depth between 0 and 8 inches and have an area between 2 and 6 and so on. And it will go through the database and basically figure out what the matching sections are for you. Here's a bending capacity check. So you'll put in all the different properties. It will do the check for you and tell you what the failure mode. Same for compression and shear, you can do that, or for even PMM interaction. So that's useful. So to give the summary here, Navigator, I think it provides a pretty flexible, user-friendly graphical user interface. It's a great tool to get started, especially if you're just picking up OpenSees and then you like to see something graphical and do some simple problems. I think it's a great tool to get started with. Another nice thing, if you are interested in hybrid simulation, maybe some of you in here, it does all that too. I didn't show that today, but there's a whole menu to define all the different parts you will need in a hybrid simulation. It has these design toolboxes built in, and like I said, it's both available as P-code and we have it for 32-bit and 64-bit machines, or you can download self-executable versions for Windows or for Mac. So yeah, you can go on the website. I might just update it over the next few days. I was just trying to catch up with a few new materials that made it into OpenSees to make them also available in Navigator. So I'll probably put up a new version in the next few days or so. So with that, thanks for the attention and thanks for staying so late, everybody.
So how much geotechnical capacity do you have over there?
How many what?
How much geotechnical power do you have over there? I'm a geotech, that's why I'm asking.
For geotechnical?
Yes. What can you do?
What can I do?
Yes.
It's pretty powerful, I would say. I mean, try it out. I mean, it's
You do stage construction? Can you do stage construction?
staged construction.
Yes.
I doubt it.
Okay.
I doubt it. We have, I mean, with the geotechnical, you have these parameters. Like I said, I'm less familiar with the geotechnical side because it was the postdoctoral student that was here that did all this. So I'm trying to answer your question, but I think like the different stages that you have in geotechnical problems, we have that available through the geotechnical parameters when you define your analysis cases, if I'm not mistaken. But I'm not 100% sure if that will do stage construction.
Nothing, you have to remove elements. You have to remove elements.
You have to remove the elements. That would probably be tricky, yeah. I don't think, yeah, I think that will probably hit the limit of what we can do.
Thank you.
Yeah.
You write software for geotechs.
Oh, there we
Your competition.
Oh, there we go.
But that's not a Navigator problem, that's an OpenSees problem.
No, we can do it. We can do it in OpenSees.
You can?
It's just not in the Navigator.
Yeah, we can.
In fact, you know, Andreas, I think, is it fair to say that if you have really finite element code, by that I mean brick elements and shell elements,
Right.
then I would suppose that it's probably better to use some kind of commercial post-processor or pre-processor, is that fair to say?
Yeah, it gets slow especially. I mean, that's probably the biggest problem.
I mean, can you display, for example, stress fields in the shell, or the shell element?
Yeah, so we can do
Okay.
that.
You can do contour plots of stress.
You can, contour plots are easy, yeah, so that's easy. It's really, problem becomes that it gets really slow. It's like, especially if you have a big model, lots of shells, lots of bricks or something like that. It's just MATLAB gets very slow.
Sure.
Do you have any feeling about the capacity in terms of memory? Because I did the same thing in GID, but when I try to model the like 3D container elements,
Yes.
like
Yeah, then you have to decide how far out you need to model your soil, and then it can get very big very quickly. So like that nuclear power plant model that I was showing you, that's about how far we can go with this, and it gets already kind of slow, and it's a bit painful, I have to say. Any other questions?
could it generate the Tickle code?
It generates the Tickle code, so you could always just use the Tickle code, yeah. And it subdivides it nicely up, so it generates, instead of generating one big Tickle file, it will generate about 10 files, I think, more or less. So it will generate one file for the geometry, where all your nodes are, another one where all your masses are, one where all your materials are defined, all the sections, all the elements, inception.